A solar proton event, or proton storm, occurs when particles emitted by the Sun become accelerated either close to the Sun during a flare or in interplanetary space by CME shocks. The events can include other nuclei such as helium ions and HZ ions. These particles cause multiple effects. They can penetrate the Earth's magnetic field and cause ionization in the ionosphere. The effect is similar to auroral events, except that protons rather than electrons are involved. Energetic protons are a significant radiation hazard to spacecraft and astronauts. Description: solar protons normally have insufficient energy to penetrate the Earth's magnetic field. However, during unusually strong flares, protons can be produced with sufficient energies to reach the Earth's magnetosphere and ionosphere around the North Pole and South Pole. Protons are charged particles and are therefore influenced by magnetic fields. When the energetic protons leave the Sun, they preferentially follow the Sun's powerful magnetic field. When solar protons enter the magnetosphere where the magnetic fields are stronger than solar magnetic fields, they are guided by the Earth's magnetic field into the polar regions where the majority of the Earth's magnetic field lines enter and exit. Energetic protons that are guided into the polar regions collide with atmospheric constituents and release their energy through the process of ionization. The majority of the energy is extinguished in the extreme lower region of the ionosphere. This area is particularly important to ionospheric radio communications because this is the area where most of the absorption of radio signal energy occurs. The enhanced ionization produced by incoming energetic protons increases the absorption levels in the lower ionosphere and can have the effect of completely blocking all ionospheric radio communications through the polar regions. Such events are known as polar cap absorption events. These events commence and last as long as the energy of incoming protons at approximately greater than 10 MeV exceeds roughly 10 pfu at geosynchronous satellite altitudes. The more severe proton events can be associated with geomagnetic storms that can cause widespread disruption to electrical grids. However, proton events themselves are not responsible for producing anomalies in power grids, nor are they responsible for producing geomagnetic storms. Power grids are only sensitive to fluctuations in the Earth's magnetic field. Extremely intense solar proton flares capable of producing energetic protons with energies in excess of 100 MeV can increase neutron count rates at ground levels through secondary radiation effects. These rare events are known as ground-level events. Some events produce large amounts of HZ ions, although their contribution to the total radiation is small compared to the level of protons. There is no substantive scientific evidence to suggest that energetic proton events are harmful to human health at ground levels, particularly at latitudes where most of the Earth's population resides. The Earth's magnetic field is exceptionally good at preventing the radiative effects of energetic particles from reaching ground levels. High-altitude commercial transpolar aircraft flights have measured increases in radiation during energetic proton events, but a warning system is in place that limits these effects by alerting pilots to lower their cruising altitudes. Aircraft flights away from the polar regions are far less likely to see an impact from solar proton events. Significant proton radiation exposure can be experienced by astronauts who are outside of the protective shield of the Earth's magnetosphere, such as an astronaut in transit to, or located on the Moon. However, the effects can be minimized if astronauts are in a low Earth orbit and remain confined to the most heavily shielded regions of their spacecraft. Proton radiation levels in low Earth orbit increase with orbital inclination. Therefore, the closer a spacecraft approaches the polar regions, the greater the exposure to energetic proton radiation will be. Astronauts have reported seeing flashes or streaks of light as energetic protons interact with their optic tissues. Similar flashes and streaks of light occur when energetic protons strike the sensitive optical electronics in spacecraft. The effect can be so pronounced that during extreme events, it is not possible to obtain quality images of the Sun or stars. This can cause spacecraft to lose their orientation, which is critical if ground controllers are to maintain control. Energetic proton storms can also electrically charge spacecraft to levels that can damage electronic components. They can also cause electronic components to behave erratically. For example, solid-state memory on spacecraft can be altered, which may cause data or software contamination and result in unexpected spacecraft commands being executed. Energetic proton storms also destroy the efficiency of the solar panels that are designed to collect and convert sunlight to electricity. During years of exposure to energetic proton activity from the Sun, spacecraft can lose a substantial amount of electrical power that may require important instruments to be turned off.